is the third part of Model 17, and by the end of this model, you'll be able to, given either KSP, molar solubility, or mass solubility, for a substance, calculate the other two quantities. Also, you will calculate the molar solubility in the presence of a common ion. You will predict the effect of pH on the solubility. Also, you'll predict whether a precipitate will form when the solutions are mixed by comparing the Q and KSP. Also, you will calculate the ion concentration required to begin precipitation. You will explain the effect of complex ion formation on solubility, and also you'll be able to explain the logic of identification of metals ions in aqueous solution by a series of reactions. So let's talk about the solubility equilibria. Because ionic compounds are strong electrolytes, they dissociated completely to the extent that they dissolve. When an equilibrium equation is written, the solid is the reactant and the ions in solutions are the product. And if we are talking about an equilibrium equation and equilibrium, also we need to talk about the equilibrium constant expression. That is called the solubility product constant and is represented as KSP. And as well as the other equilibrium constant is the concentration of the products over the concentration of the reactants that you may know. Now, the solubility product, we have an example here of barium sulfate. Barium sulfate in equilibrium with barium and also sulfate. This is the solid, and in aqueous solution the ions that has been dissociated from this ionic compound, and the equilibrium constant will be the concentration of barium and the concentration of sulfate. Okay, so here we have the equilibrium constant, the KSP, for this equilibrium. The solid, as we may know, they are not part of the equilibrium constant because the solid basically they are constant. Okay, so and because of that, as they are part of this KSP value, so the KSP is going to be equal for the barium sulfate to the concentration of barium times the concentration of sulfate. Also, we can have another example of barium phosphate. Here we have that the equilibrium, when we dissociate this ionic compound, we have 3 moles of bariums and 2 moles of phosphate. So the KSP for this equilibrium is equal to barium, the concentration of barium cubic, and the concentration of phosphate square. Okay, so these basically are the expressions of the solubility product constant. Now, let's make clear that solubility and solubility product are not the same thing. The KSP is not the same as solubility. Okay, so the solubility product is not the same as solubility. Solubility is the quantity of a substance that dissolves to form a saturated solution. Okay, that is the definition of solubility. And most of the time they have can be expressed in 2 different ways. One unit is gram per liter. Gram per liter, usually also known as the mass solubility, and moles per liter, usually also known as the molar solubility. So we can go, for example, from the mass solubility, that is expressed in grams per liter, to the molar solubility, that is for moles to liter, by using the formula weight, or also from the molar solubility to the mass solubility. That's the same way we can go from the molar solubility to the molar concentration of ions using the empirical formula, and from the molar concentration of ions to the KSP using the solubility in equilibrium. Okay, so let's do an example here. Let's calculate the solubility from KSP. So the solubility product, even though it's not solubility, but it's going to help us to determine the solubility of a compound. So the solubility product for calcium fluoride is 3.9 times 10 power of minus 11 at 25 degrees. What is the molar solubility? So the calcium fluoride is a solid and is an ionic compound. So the equilibrium will be the formation of the calcium ion plus 2 ions of fluoride, because we have two coefficient number 2 here for fluoride, so we have 2 moles of fluoride. So the KSP, the expression, it will be equal to the concentration of calcium times the concentration of fluoride squared. Okay, and this will be equal to the value that we have here at the beginning. So using the Rice table, because calcium fluoride is a solid, basically there is no change in the initial concentration, so we don't count with the calcium fluoride. Is not part of the KSP. For the calcium, we have a concentration of 0. And for the fluoride, we have a concentration also of 0, okay, at the beginning of the reaction, of the dissociation specifically. So the change in concentration, in this case, will be, there's no change for calcium fluoride, but for calcium will be plus X, and for fluoride will be 2X. Okay, so this will be X, this will be 2X. So in equilibrium, the concentration of calcium will be X, and the concentration of fluoride will be 2X. Now remember that the expression of KSP we have here is square. Okay, so that means that it will be 2X squared. So now if we solve by substitute the equilibrium concentration values from the table into the solubility product equation, we will have this, this value equals X, that represent the concentration of calcium, and 2X, that is the concentration of fluoride at equilibrium with a square. Okay, and we multiply this, we have 4X cubic. So now we can solve by the X, and we can determine the value of the solubility. That will be equal to 2.1 times 10 power of minus 4 molarity. This is basically the solubility for the calcium fluoride. Also, we can express this in grams per liter. So by multiply with the molar, by the molar mass, we'll have a value of solubility of 0.16 grams per liter. So this is the solubility for calcium fluoride using the units of grams, liters, or moles liter. Now, there are some factors that could affect the solubility of a solid. Let's see this example that we saw at the beginning of this model. Barium sulfate producing barium plus sulfate. If what can we do to affect the solubility, to decrease this solubility? What do you think what we can do by using just what we have here? What will happen if we add barium to this equilibrium? What will happen? It will go to the left. It will go to form more of the barium sulfate. So by adding one of this will affect the solubility of this. It will be less soluble if we have some common ion. Okay, so the common ion effect, if one of the ions in a solution equilibrium is already dissolved in the solution, the solubility of the salt will decrease. So here we have an example, the ones that we saw before, it was calcium fluoride. If either calcium ions or fluoride ions are present, then calcium fluoride will be less soluble. And here we have, this is a graphic where concentration of sodium fluoride, that this will be the one that we are going to add to the one that are in equilibrium. This is the molar solubility of calcium fluoride. This is a pretty high molar solubility, but as you can see, when we add sodium fluoride, the common ion, the solubility start to decrease. Okay, and as we increase that concentration, it is more the effect of that ion, common ion effect on the solubility of the calcium fluoride. It will decrease dramatically from this point to this point as we increase the concentration of that common ion. It could be fluoride or it could be also calcium. So any of those that you add to the system will affect the solubility of the calcium fluoride. Now let's calculate the solubility with a common ion. Okay, so what will happen to the solubility if we add some of the ions that are part of that solid. So what is the molar solubility of calcium fluoride in zero point 0.1 molar of calcium nitrate? This is the solid that we have that is in equilibrium, and from here, from this salt, we're adding the calcium. The calcium is one of the ions that is produced by this solid in equilibrium. Okay, as we can see here, calcium fluoride will dissolve and dissociate it by producing the ion of calcium and the ion of fluoride. And at the beginning, we start also with another concentration of calcium that would affect this value. Also, the KSP is the concentration of calcium, concentration of fluoride square, okay, because we have a coefficient here of 2 in the equilibrium equation. And also the KSP for this is 3.9 times 10 power of minus 11. So the initial concentration for calcium fluoride as is a solid is basically is going to be affected, okay. For calcium, the initial concentration is going to be 0.1 because now we have added this at the beginning. And for fluoride, we didn't have any concentration for it. Then the change in the concentration for calcium will be plus X, for fluoride will be plus 2X. And at equilibrium, this will be 0.01 plus X, and this will be plus 2X. So now we can substitute these expressions at equilibrium in the constant of KSP, okay, to determine the value of the solubility of X. So by doing that, now we can substitute those values here. 3.9 times 10 power of minus 11 is equal to 0.0 plus X. This is the concentration of calcium, the expression at equilibrium, and the 2X is the concentration at equilibrium of fluoride, and the square is part of the expression of KSP. So now we can assume that this X is really small, okay, less than 0.01. So this will not affect this value, okay. This one will affect this one, but this is not going to affect this one. So that means that this is equal to 0.01, okay. So we basically simplify this equation, and now we can determine the value of X by doing the square of this and then all the other mathematical process. And we have that the solubility is 3.1 times 10 power of minus 5 molar. So in the previous example, we determined the solubility of the calcium fluoride without the common ion effect. And that solubility was 2.1 times 10 of minus 4 molar. So we can see here that the concentration, that the solubility or the common ion effect is affecting the solubility of calcium fluoride because it's decreasing that solubility, minus 5, as here that is minus 4 when it's without the common ion effect. Also, there are other factors that could affect the solubility. For example, the pH. If a substance has a basic anion, it will be more soluble in an acidic solution because it will be a reaction of acid-base reaction, a neutralization type of reaction. Remember that buffers control pH, so when a buffer is used, there is no change in concentration of the hydroxide ion. Also, here we have, for example, a solid that is lead fluoride here, and when we add acid, the acid will react with the fluoride ion, and because of that, it will decrease the concentration of this, so this will release more of the fluoride, and because of that, it will make more soluble, okay, the lead fluoride in the presence of acid. Okay, so the acid will react with the fluoride to produce HF, that is a weak acid, and because this is a weak acid, it will be in equilibrium, so you will have this in solution, decreasing the concentration of fluoride in solution and making this to release more of the fluoride to keep that concentration constant. So the acid will affect the solubility of this of lead fluoride. What happens if we have, for example, the contra ion will be an iodide. The iodide with acid, it will produce HI, but the HI is a strong acid and it will be dissociated completely. So because of that, the adding of acid is going to have no reaction. You're going to have basically the same solid here. It's not going to affect the solubility because this an ion, when react with H, is going to produce a strong acid that will be dissociated completely, and because of that, it's not going to affect the concentration of the iodide. So that because of that, it's not going to affect the solubility of the solid. Another factor that could affect the solubility of a solid, it's called a complex ion formation. So, for example, we have here the silver chloride, a solid, and this is an equilibrium producing the silver ion and the chlorine. So, the silver ion here, we can see that is positive. So that means that it can receive electrons. So it will be played as a Lewis acid. So if we have a Lewis base, okay, so if we have a Lewis base in solution as NH3, NH3, remember that we have here a lone pair electrons that could uh, be given these electrons to the silver. So that's why this will be the Lewis acid and this will be the Lewis base. And by that, it will be producing the diamine silver. Okay, this is the diamine silver. And as you can see here, this um, ammonium is reacting with the silver. So what is happening with this equilibrium as we are consuming this ion of silver? Is switched to the right. Okay, this, the equilibrium is displaced to the right, so making the solid more soluble. Okay, so this complex ion formation increase the solubility of the silver chloride. So the formation of these complex ions increases the solubility of these salts. So basically, this is a list of different metal complex that could be formed. Okay, but these are basically the Lewis bases that has been added to the system that was in equilibrium. And basically, here we can see the product of those complex ions. So, how complex ion formation affects solubility? So, we have silver chloride that is insoluble, as we mentioned before. The Ksp is 1.6 times 10 powers minus 10. This is pretty insoluble. But when we add NH3, the NH3 acts as a Lewis base and the silver as a Lewis acid. So this will increase the solubility of silver by forming the complex ion with ammonium. So here we have silver chloride in the bottom, and we're adding amounts of NH3 to the solution, and slowly it's reacting and making it more soluble, and we add enough ammonium to react with all of the silver in the system. You will see that it make all the silver chlorides totally soluble. Okay, so this complex ion increase the solubility of the solids. Amphoterism and solubility. There are some compounds that are known to be amphoterics, specifically oxides and hydroxides. And these compounds are soluble in strong acids or base because they can act either as acids or base. So this type of compounds, because they can react in either acid or base, they are called amphoteric. They can play the role of an acid or they can play the role of a base. Some examples of this oxides and hydroxides are with aluminum, chromium, zinc, and tin. Let's use the example of aluminum. We have aluminum hydroxide, and as you can see here is insoluble. Okay, now when we add acid to this system, it's completely soluble. As we can see here, we have aluminum and OH, and we add acid. What type of reaction do you think are between this amphoteric hydroxide and the acid? An acid base. Remember, the hydroxide is a base. So here we have the reaction of acid base reaction that dissolve the aluminum hydroxide. Okay, so here we have the aluminum plus 3 water producing the acid. Actually, basically is the aluminum hydroxide reacting with the acid to produce water and aluminum. Okay, so that's why it dissolved in an acid. And what happened with the aluminum hydroxide in OH? If we add OH, this is not an acid, so this can act like removing a hydrogen from here, okay? But aluminum is a Lewis acid, and hydroxide is a Lewis base. So those electrons can be donated to the aluminum, producing the ion complex that we saw in the slide before. And the adding of a basic solution is also makes soluble this aluminum hydroxide. And this is all because of the solution due the complex ion formation. Okay, so here the aluminum hydroxide react with OH, producing the complex ion. And this complex ion, as we saw before, reduce also the solubility of a compound. If there is any way that we can know if a precipitate is going to form or not, yes. To decide, we calculate the reaction coefficient as Q that we did before and compare it to the solubility product constant KSP. Remember that this Q is when you are comparing concentration and you don't know if you're at equilibrium. Okay, so it's the same concept, products over reactants, and you compare that calculation to the KSP. And for example, if Q is equal to KSP, the system is at equilibrium and the solution is saturated. Okay, and if Q is lower than KSP, more solid can be dissolved, so no precipitate forms. But if Q is larger than KSP, then a precipitate will form. So the only way that you can know if you're going to have a precipitate is when the Q is larger than the KSP.